Hi everyone. In this lecture, we will study coloring. Two type of coloring we will study: vertex coloring and edge coloring. Okay, what is this concept of coloring? So let's start with this. First, we will start with vertex coloring. What is the concept of vertex coloring? So you can notice that, see, the definition is very simple. We just have to apply the definition. So please read the definition. Give neighbor vertices different colors. This is the concept of vertex coloring. So we want to color the vertices. To every vertex, we want to give a color. But remember, what should happen? That neighbor vertices, adjacent vertices, they should get different colors. So this is the definition. So let's see the definition of vertex coloring. Vertex coloring, the definition is very simple, that a graph coloring, or I can say vertex coloring, by default, let me tell you, there are two types of coloring. Yes or no? One is vertex coloring, another is edge coloring. Okay, so first we will study vertex coloring. And by default, when I say graph coloring, when I say graph coloring, or by default, when I say coloring, then what it means? It means vertex coloring. It does not mean edge coloring. It means vertex coloring. So by default, coloring means vertex coloring. By default, graph coloring means vertex coloring. Okay. So first we will study vertex coloring, and then we will study this edge coloring. So let's see the concept of vertex coloring, or I can say graph coloring. What is that? This is basically, you are assigning colors. Okay, you are assigning colors to the vertices, such that to the vertices we want to give colors such that no two adjacent vertices share the same color. See, read this: no two adjacent vertices. Okay, so no two adjacent vertices, they have the same color. This is the definition. So just focus on the definitions, read the definition, and this is your concept. We have to analyze this concept now. Okay, so the concept is actually very simple. So for example, if you have a graph, like for example, if you have this graph, okay, now what we want to do, we want to do vertex coloring, means the adjacent vertices, they should get different colors. For example, here these vertices are adjacent, so they should get different colors. These two, can they get same color? Can they get same color? These two, can they get same color? Yes. Okay, we don't care about them. They can get same color or different color. We don't care about them. Okay, we don't care about them. So is this clear? See, we only care about adjacent vertices. Adjacent vertices, they should get different colors. For example, if I give red color to this, then I should not give red color. Okay, because they are adjacent. So adjacent vertices should get different colors. If I give red color here, green color here. But remember, I don't care about non-adjacent vertices. For example, this vertex and this vertex, they are non-adjacent. They are non-adjacent. So if I give red color here, I can give red color here, or I can give green color here. That is my choice, like whatever I want to do. Okay, so this is the idea. Graph coloring means, read the definition. Graph coloring means no two adjacent vertices should get same color. We only care about adjacent vertices. We don't care about non-adjacent vertices. So if two vertices are non-adjacent, like okay, like this vertex and this vertex, these two vertices are non-adjacent, so I can say they, okay, we don't care about them. They can get same color or they can get different color. We don't care about them. But the adjacent vertices, they should get different colors. They should get different colors. So you can notice this is a graph coloring. In this diagram, can you notice in this diagram that the you can notice the adjacent vertices, they have different colors. For example, these two vertices are adjacent, they have different colors. These two vertices adjacent, they have different colors. See, they are not adjacent, so they can have same color. They can have, for example, these two are also not adjacent, these two, so they can have same color, different color. We don't care. Okay, but remember, if you have adjacent vertices, they should get different colors. You can notice adjacent vertices, they have different colors. These two are adjacent, they have different colors. These two are adjacent, they have different colors. So is the definition clear? Let me know. Let's see this example. For example, this graph same. These two graphs are same basically. Okay. Now you can notice here that adjacent vertices, they have different colors. Yes or no? For example, these two vertices are adjacent. Notice that these two vertices are adjacent and they have different colors. These two vertices adjacent, they have different colors. They have different colors. Okay, so adjacent vertices should get different colors. This is the definition. Is the definition clear to everyone? What is a coloring? Coloring means color the vertices. To the vertices, we want to give the color such that no two adjacent vertices should get same color. This is called coloring, or you can call it proper color. Okay, so both are same. You can call it proper coloring, or you can call it coloring. So both are same. So what is the idea? Color the vertices such that no two adjacent vertices they get the same color. For example, here, tell me one thing. If I give red color to this vertex, tell me one thing. If I give red color to this vertex, if I give red color to this vertex, can I use this red color here? Can I use this red color here? No, because they are adjacent. Okay. Remember, adjacent vertices should get different colors. Adjacent vertices should get different colors. So I need to give some different color. Okay. Now tell me, can I give this yellow color here? Can I give this yellow color here? No. Okay. So can I use this red color here? No, because they are adjacent. Adjacent vertices should get different colors. So finally, what I can do, I can give basically, I can give this color. I can. Okay. So for example, I can give this color. Okay. So this is the idea. So, okay, idea is very simple that adjacent vertices should get different colors. Okay. This is the definition of coloring, or you can say vertex coloring, or I can say, so by default, you can call it coloring. You can only call it coloring, or you can call it vertex coloring, because I told you by default coloring means vertex coloring. By default, okay, you can call it graph coloring, because I told you that by default graph coloring means vertex coloring. Okay. And so this is the idea, coloring, vertex coloring, or I can call it proper vertex coloring. Another name is proper vertex coloring, or I can say proper coloring. I can say proper coloring. Okay. Proper coloring, proper vertex coloring. So what this means, this simply means that every pair of adjacent vertices, if two vertices are adjacent, okay, every pair of adjacent vertices should get different color. Okay, must get different colors, different color or label. Different, either you can call it color or you can call it label. So they must get different colors. Okay. So for example, here, this graph is same as this graph. These two graphs are basically same. They are isomorphic to each other. Okay. These two graphs are isomorphic. So let's see here. Is this proper coloring on your screen? Look at this. Is this proper coloring? Tell me. Is this proper coloring? Yes, this is proper coloring, right? Okay. So this is proper coloring because you can notice that adjacent vertices have different colors. Okay, no two adjacent vertices, they have same color. Can you notice? Okay, so that's the simple idea. So now let's see the next concept. Okay, tell me one thing. Tell me one thing. If I give you this graph like A, B, C, D, and if I ask you to color this graph, what is the most trivial thing? If I ask you to proper color this graph, what is the most trivial without using your brain? What is the most trivial solution you will give? Most trivial solution you will give? Four colors. Yes. What you will say? You will say to every vertex give different color. Okay. Why bother, right? Okay. Very trivial solution. What will be the trivial solution? Like what will be a trivial solution? So the trivial coloring, I can say. What is a trivial coloring? You can simply say that to every vertex you give different color. Okay, every vertex different color. Every vertex different color. This is the trivial solution. This is the trivial coloring. What you can do, every vertex you can give different color. So for example, color number 1, color number 2, color number 3, color number 4. Okay, this is the trivial solution. Now you can notice, because every vertex have different colors, so I can say that adjacent vertices, they don't have same color. You can notice adjacent vertices, like they are adjacent vertices, they have different color. Adjacent vertices have different color. This is the trivial coloring. So I can say that this graph is 4 colorable. So I can say this graph is 4 colorable because you can color it using 4 colors. Can I say this is 4 colorable? 4 colorable. Can you color it using 4 colors? Yes. Yes, you can color it using at most 4 colors. This basically means at most 4 colors you will need. Okay, so this is 4 colorable. Now let's see this same graph. Is it three colorable? This same graph, is it three colorable? Is this graph three colorable? Can you give a three coloring for this? Is this graph three colorable? Can I color this using three colors? Yes. What I can do, I can give color number 1 here, or maybe color number red here. Okay. Now I cannot give color number red here. I have to give color number green here. Then what I can do? I can do color number blue here, and I can do green color number red here. Okay. So this is the idea. So is this three colorable? Yes. Is this graph three colorable? Three colorable, because using three colors you can do it. Okay. So this graph is three colorable also. Okay. Remember what K colorable means. What K colorable, whenever we say K colorable, what that means. K colorable means, it means using at most K colors you can do it. Okay. K colorable, it means you can color it using K colors. It means basically using at most K colors. Using at most K colors. At most K colors. Okay. Using at most K colors you can color it. Okay, we can color. This is the definition of it. Okay. So you can notice. See, can I give this red? Can I give this color red? Like red here, red here. Can I give this? Yes, because they are non-adjacent. We don't care about non-adjacent vertices. We only care about adjacent vertices. Adjacent vertices should get different color. Adjacent vertices, they get different color. We don't care about non-adjacent vertices. The non-adjacent vertices we don't care about. But adjacent vertices, they must get different color. So what is the definition of K colorable? K colorable means using at most K colors. Using at most K colors, can you color it? Tell me, is this graph one colorable? Is this graph one colorable? This graph. Is this graph one colorable? Like, can I color this graph using one color? Is this graph one colorable? So the answer is no. Just think about it. If I give same color to everyone, one colorable means you can use only one color. So this graph is definitely not one colorable. So this is not a coloring. This is not a proper coloring. This is not a proper coloring. Or I can say this is not a coloring. So I can simply say that this is not correct. Okay. This is not a coloring. This is not a proper coloring, because you can notice adjacent vertices, they have same color. These two adjacent vertices, they have same color. So I can say, is this one colorable? The answer is no. Now, is this two colorable? Is this graph two colorable? Can I color this graph using two colors only? At most two colors. Yes, because what you can do, see, if I use red color here, okay, if I use red color here, now I cannot use red color here and here. I cannot use. So let me use yellow color here, yellow color here. See, let me use yellow color here. Now I can reuse color yellow here, because they are, okay, there is no problem. I can reuse, because you can notice this is red. So they have adjacent vertices, they have different color. And here also what I can do, I cannot use yellow color. I cannot use yellow color, but I can use red color. So this is the idea. Okay, so is this two colorable? Yes. Can you notice for this graph, what is the minimum number of colors required? For this graph, what is the minimum number of colors required? Like if I ask you minimum number of colors, what is that? Minimum number of colors needed. That is 2. 2 is the minimum number of colors needed. So I can say this is chromatic number. This is your chromatic number, means minimum number of colors needed. This is called chromatic number. This is known as chromatic number. Chromatic number means what is minimum number of colors needed? Minimum. How many minimum colors you need? That is the chromatic number. Is this clear, the definition? So let's see the definition of K coloring. K coloring means at most K colors you will use. Okay, so this is the idea. K coloring, that simply means using at most K colors, can you do it? Using at most K colors, can you do it? Okay, so what is K colorable? K colorable means at most using, okay, at most K colors. Can you color using at most K colors? Okay, so this is the idea. But for example, this graph, tell me, can I say this graph is 6 colorable? Can I say this graph is 6 colorable? Look at this graph. Can I say this is 6 colorable? The answer is yes. Can I say this is 10 colorable? Can I say this is 10 colorable? Can I say this is 10 colorable? The answer is again yes. Are 10 K colorable means at most K colors. K colorable means can you do it using at most K colors? A graph is K colorable if you can do it using at most K colors. So using at most 10 colors, can you do it? Yes. Is this clear? See, K coloring, look at this, K coloring, K coloring. K coloring means using at most K colors, can you do it? Using at most K colors, can you do it? Like using at most 2 colors, can you do it? Using at most 1 color, can you do it? So is this 10 colorable? Yes. Is this 100 colorable? Using at most 100 colors. At most 100 colors you can use. At most 100 colors you can use. Is this 100 colorable? Yes. Okay. Tell me one more thing. Let's see. Is this 5? Is this a 5 colorable? Okay. So this is 6 colorable. This is trivial, right? This is trivial. 6 colorable is trivial because you can give different colors to every vertex. Okay. To every vertex you can give different. Let's see this 5 colorable. Is this 5 colorable? Can you do it using at most 5 colors? Okay, let's see. Can you do it using at most 5 colors? This is what we have to check. So see what, okay, tell me one thing. You tell me one thing. If I give color number 1 here, if I give color number 1 here, can I give this color number 1 here? No, because they are adjacent. So I have to give color number 2 here. Can I reuse color number 1 or 2 here? Can I reuse color number 1 or 2 here? Can I reuse? Okay, I cannot reuse. I cannot reuse. So I need color number 3 here. I cannot reuse because they are, this is a triangle, this is a cycle. Okay, so they are adjacent to each other. Okay, can I reuse any of these color? Can I reuse any of these color? Can I reuse? Can I reuse? No, I cannot reuse. So I need another color. Okay, I need another color. Now, so I can give color number 5 here and I can give, can I reuse color number 2? Can I reuse color number 2? Yes. So this is 5 colorable. Yes, this is 5 colorable. So this graph is 5 colorable. Is this graph 4 colorable? Is this graph 4 colorable? Can we color this graph using 4 colors? So let's see. So you can notice one thing. If I give color number 1 here, I cannot give color number 1 here. So let me give color number 2. For this vertex, I cannot reuse these 2 colors. So let me give color number 3. Now these 3 colors I cannot use for this vertex. So let me give color number 4. Now, is this 4 colorable? Like, can I reuse? For example, can I reuse color number 1? Yes, I can reuse. Can I reuse color number 2? Yes, I can reuse. So is it 4 colorable? Yes, this is 4 colorable. Is this graph 3 colorable? Is this graph 3 colorable? This graph. Can you color it using 3 colors? Okay. Can you color it using 3 color, at most 3 colors? At most 3 colors you can use. Okay, at most 3 colors you can use. You cannot do it. Just check it. Just look at this area. Just look at this area. This is a K4. Can you look at this area? This is a K4. Every vertex is adjacent to another vertex. Can you color this graph using 3 colors? At most 3 colors. At most. Okay, just notice one thing. If I give color number 1 here, I cannot reuse this color in this area. In this area, I cannot reuse because they are adjacent. Because they are adjacent. So I cannot reuse this color. Okay. So here I have to give color number 2. I cannot reuse this color number 2 in this area because this is complete graph for 4 vertices. Every 2 vertices are adjacent. I cannot reuse. I cannot reuse. I cannot reuse because you can notice they are adjacent. So I have to give different colors to every vertex. So minimum 4 colors I need. So is this 3 colorable? The answer is no. This is not 3 colorable. I can say minimum 4 colors you need. Minimum. Okay, so tell me minimum how many colors you can do. So this is 4 colorable and this is the minimum number, right? This 4, if you notice, this is the minimum number of colors needed. This 4 is the minimum number of colors needed. Colors needed. Okay, so this 4 is basically the called chromatic number. So this 4 is called chromatic number. Chromatic number means minimum how many colors you need. So this 4 is your chromatic number. So what is chromatic number? Chromatic number is 4 and the symbol is zeta, zeta, whatever. Okay, so this is the symbol. This is the symbol. So what is the name of this symbol? So let me tell you that the name of this symbol is zeta. And this is your, so I can say this is the idea. And the name is zeta. Zeta. Okay, zeta, zeta, whatever. Like this. So zeta of G. This is the chromatic number, remember. So what is chromatic number? That is minimum number of colors. How many minimum number of colors you need? That is the chromatic number. So for this graph, chromatic number is 4 because you can do it using 4 colors and you cannot do it using 3 colors. Okay, is this clear to everyone? So what is a trivial solution? You know, trivial solution means give different color to every vertex. What is a chromatic number? So what is the interesting problem? This is not an interesting problem. If I ask you maximum how many colors you need, that is not interesting, right? But if I ask you minimum how many colors you need, minimum possible. If I ask you how many minimum possible colors you need, so that is interesting problem. And this is called chromatic number. This is known as chromatic number. For example, in this graph, can I say this is 3 colorable? This graph, is it 3 colorable? Yes, this is 3 colorable. You can notice green, red, blue. So this is 3 colorable. But what is the chromatic number? Minimum how many colors you need? Minimum 2 colors you need. You can notice. Can I do it using 1 color? Can I do this graph using 1 color? No, I cannot use. Okay, I cannot use 1 color. Okay, so the chromatic number will be 2. Minimum 2 colors you need. So this is the idea. But remember this graph, I can say this graph is 3 colorable. I can say this graph is a 3 colorable because at most 3 colors you need. This graph is 3 colorable. And the chromatic number is minimum these many color you need. So what is the chromatic number of a graph? Chromatic number of a graph, that means what is the minimum possible number? Minimum possible number of colors that you need. Okay, so this is the symbol is zeta of G. Now let's see. So yeah, we have seen the definition of chromatic number, and this is very important concept. Chromatic number means minimum number of colors needed. Minimum how many colors you can use. Okay, so that is the idea. Remember K coloring. What is the K colorable? K colorable means at most K colors. K colorable simply means at most K colors. And the smallest value of K, that is your chromatic number. Let's move on. So so this graph we have already seen, and you can notice that this is 4 colorable. So for this graph, the chromatic number will be 4. You can notice. Okay, so this is the idea. Now let's see one by one for many different graphs. So remember, if a graph is K colorable, what that means? K colorable means if you can color using at most K colors. This is the K colorable. And minimum number of colors that you need, that is your chromatic number. This is the minimum number of colors you need. Now let's see. First we will see for complete graph. What can you say about complete graph? One by one, let's see every graph. What is the chromatic number? Remember, chromatic number is interesting problem. So let's see the chromatic number of complete graph. What will happen to the complete graph? If your graph is complete graph means Kn. Kn means complete graph on n vertices. Okay, so this is your complete graph on n vertices, where every 2 vertices are adjacent. So this is a complete graph on n vertices. So there are total n vertices and every 2 vertices are adjacent. So how many colors? What is the chromatic number? What do you think? Minimum how many colors you need? What is the chromatic number of Kn? The chromatic number of Kn will be, tell me one thing, can you reuse in this Kn? Can you reuse a color? Can you reuse a color? You cannot reuse a color. Okay, so that is the reason chromatic number will be n, because notice you cannot reuse. If I give you, for example, if I give you this graph, this is your K1, and the chromatic number here is chromatic number for this graph, that is 1. Okay, because you can give red color here, you can give red color here, so this chromatic number is 1. Next, if I have this graph is K2, and here the chromatic number will be what? That will be, because you cannot reuse. If I give red color here, I cannot give red color here. I cannot give. So you cannot reuse the colors. Okay, next, this is your K3. This graph is K3. This is your K3. You cannot reuse a color. You can notice if I give red color here, I cannot give red color here because every 2 vertices are adjacent. Okay, you cannot reuse a color. If I give red color here, You cannot give red color here. You cannot give red color here. So that is the idea. I have to give different colors. I have to give. So for this graph, the zeta will be 3. So this is the simple idea that if you have a complete graph, okay, like you have these vertices. Okay, let's assume these vertices you have like 1, 2, 3. Okay, these vertices like A1, A2, A3, and so on. Like A1, A2, A3, and so on, AN. So these are your vertices. Now for these vertices, you can notice that you cannot reuse a color. This is the thing you should notice, that you cannot reuse a color. Okay, in Kn we cannot reuse a color. We cannot reuse a color because every two vertices are adjacent. So we cannot reuse a color. If you reuse a color, then what will be the problem? Just think about it. We cannot reuse a color. Why? Because if you reuse a color, let us assume you reuse like this. Okay, let us assume you reuse like this, red here, red here. Okay, if you reuse, then what is the problem? What is the problem? Because this is a complete graph, so every two vertices are adjacent. Every two vertices are adjacent, so you cannot reuse a color. So that is the reason every vertex should get different color. Okay, so the chromatic number for complete graph, that will be n. So if you see a complete graph in your life, okay, whenever you see a complete graph, then immediately you know that if you have a complete graph on n vertices, definitely n colors is definitely needed whenever you see a complete graph. Let's see the next graph, that is ageless graph, En. This is your favorite ageless graph. Okay, so you have ageless graph. This is the ageless graph on n vertices. So here, what will happen for this graph? What is the chromatic number? So only one color is enough because here there is no age. So there are no adjacent vertices. So the only one color is needed. Okay, so I can say the chromatic number will be 1. Minimum only one color is needed. To every vertex, you can give same color. Okay, so for example, if you have E4, then this is your E4, A, B, C, D. This is the E4. Then what you can do? You can give same color to the every vertex. You can give same color to every vertex. Very simple. To every vertex, you can give same color. Same color you can give. So this is the ageless graph. Now let's see the next graph, that is path graph. What will happen to the path graph? Pn. What will happen to the path graph on n vertices? For example, if you have P3, then what will be zeta? If you have P3, then what will be the chromatic number? What you can do, minimum how many colors? See, very simple. If you give color number 1 here, you can give color number 2 here. You can reuse. Again, you can reuse, right? Okay, so very simple. See, if I give color number 1 here, I cannot give color number 1 here. So let me give color number 2. I can reuse the color number 1 again. So here the zeta will be 2. Okay, if you have P2, then also zeta will be 2. If you have P4, if you have P4, then also zeta will be 2. Then also chromatic number will be 2, because you can give color number 1 here. You cannot give color number 1, but again you can reuse. And again you can reuse color number 2. You can reuse. Okay, so very simple. So the zeta will be 2. So any graph you take, if you have any Pn, then what will be the chromatic number? Minimum 2 colors is enough. So this is the chromatic number. Is this clear? Only 2 colors are enough. You can reuse. I am asking chromatic number. Chromatic number means minimum how many colors you need. I am asking chromatic number. I am asking chromatic number. Chromatic number means minimum how many colors you need. Minimum colors needed. So whatever graph you, okay, so that is the reason. But remember for P1, what will happen? For P1, if you have this graph P1, for P1 the chromatic number will be 1. For P1 the chromatic number will be 1. So here when n is greater than equal to 2, then chromatic number will be 2. Is it clear to everyone? Let me know. Let's see the next category of graph. The next category is, so this is 3 and this is 4. The next category is cycle graph. What about cycle graph? So you can notice this is your C3, this is your C4, this is your C5, this is your C6. So tell me what I can do for cycle graph. This is C3. So I need chromatic number is 3. Okay, because this is a complete graph. So every vertex should get different color. And here you can, what you can do in C4, what you can do, I can give color number 1 here. I cannot reuse color number 1 here. So let me give color number 2. Can I reuse color number 1 here? Yes. Okay, so can I reuse color number 2 here? Yes. So for C4, the chromatic number will be 2. And for C5, the chromatic number will be again 3. Because if I give color number 1 here, I cannot give color number 1 here. So I can give color number 2. I can reuse color number 1. I can reuse color number 2. But notice, I cannot reuse color number 2. I cannot reuse color number 1. So I have to give color number 3. Okay, and what about this C6? This C6. For this chromatic number will be 2. Because what you can do, color number 1, color number 2, 1, 2, 1, 2. Okay, so this is the idea. For a cycle graph, what will happen? For a cycle graph, the answer will be 2 when n is even. When n is even. Okay, so the chromatic number will be 2. I can say the chromatic number will be 2 when n is even, and the chromatic number will be 3 when n is odd. So this is very simple. Let's see the next category of the graph. That is the bipartite graph. What do you think about bipartite? What do you think? What is the bipartite graph chromatic number? Some students are saying 2. Some students are saying 2. Tell me, is this bipartite graph? Is this bipartite graph E3? Is this bipartite graph? Some students are saying 2. Is this bipartite graph? This is not bipartite. This is a bipartite graph. Yes, this is a bipartite graph. This is bipartite, right? Bipartite means you can create 2 partition. Yes, I can create 2 partition A, B, C. I can create 2 partition C. I can create 2 partition. And you can notice there is no edge here. You can notice there is no edge here. So this is correct. There is no problem. So this is a bipartite graph. We have already seen in the bipartite graph. I told you bipartite means there is no odd cycle. A graph is bipartite if and only if there is no odd cycle. A graph is bipartite if and only if, just use this. A graph is bipartite if and only if there is no odd cycle. If and only if there is no odd cycle. So you can notice there is no odd cycle here. You don't have any odd cycle here. So this graph is bipartite. You can create 2 partitions, you can create. And you can notice there is no edge here, there is no edge here. So this is a bipartite graph. What is the chromatic number for this bipartite graph? That is 1. Okay. So tell me, if I have this bipartite graph, for example, if I have this type of bipartite graph with at least 1 edge, if I have a bipartite graph with at least 1 edge, if I have, then what will be the chromatic number? If I have at least 1 edge, see, if I have at least 1 edge, then the chromatic number cannot be 1. Yes or no? The chromatic number cannot be 1. Now the chromatic number will be 2. Why the chromatic number will be 2? Because see, there is no edge here. These are non-adjacent. All these vertices are non-adjacent. So I can give same color to them. I can give color number red here. Okay, I can say this is the red class. I can say this is the red class, and I can say this is the blue class. Because these are also non-adjacent. So finally, I can say that these are non-adjacent, so I can give same color them, and these are non-adjacent, I can give same color to them. And you can notice that every edge will have different colors. Yes or no? Every edge will have different colors at their end point. So you can notice. Yes or no? So very simple, the chromatic number will be 2. I can say one thing. I can say for bipartite graph, what will be the chromatic number? If I directly ask you the bipartite graph, the chromatic number, that will be less than equal to 2. Means I can say bipartite graphs are too colorable. Remember, bipartite graphs are too colorable. Bipartite graphs are too colorable because you need at most 2 colors. Are too colorable. but chromatic number is what? The chromatic number is less than equal to 2. Okay, remember 2 colorable. That simply means chromatic number is less than equal to 2. If a graph is k colorable, then what can you say about chromatic number? If you know G is k colorable, then what can you say about chromatic number? If you already know G is k colorable, then what can you say about chromatic number? Chromatic number means minimum how many colors you need. Minimum how many colors you need. You already know it is k colorable, so minimum you need minimum how many colors you need? I can say, sorry, at most k colors you need. Yes or no? So the chromatic number will be less. If you already know the graph is k colorable, it means chromatic number will be less than equal to k. Okay, so here you can notice bipartite graph is 2 colorable. It means chromatic number will be less than equal to 2. Bipartite graph with at least one edge. Okay, there are two type of bipartite graph. Okay, bipartite graph with no edge. So if you have bipartite graph with no edge, either your graph does not have any edge, means your graph is basically edgeless. Your graph is edgeless. So this is your graph En. So what will be the chromatic number? Then the chromatic number will be 1. And if your bipartite graph has at least one edge, only two cases are possible. Your bipartite graph with at least one edge. At least one edge. So if you have at least one edge, then you cannot use one color. If you have at least one edge, then you cannot use one color. So I can say the chromatic number will be 2 here. So that is the reason chromatic number is less than equal to 2. Is it clear to everyone? Anyone has any doubt in this? If any graph has at least one edge, then what can you say about this? If any graph, if G has at least one edge, if G has at least one edge, if G has at least one edge, then what can you say about chromatic number? What can you say about chromatic number? That will definitely be greater than equal to 2. Chromatic number will definitely be greater than equal to 2. If your graph has, I can say, this is the idea. So let's see. So we have seen the Kn, we have seen edgeless graph, we have seen bipartite graph, we have seen. So bipartite graph with at least one edge, they have chromatic number 2. The sixth category, the complete bipartite graph, KMN. Okay, so what can you say about KMN? Where M is also greater than equal to 1 and N is also greater than equal to 1. So let's assume M is greater than equal to 1, N is greater than equal to 1. For this, again, this is a bipartite graph. And if you have at least one edge, then the answer will be 2. If you have at least one edge, then the answer will be 2. So the chromatic number will be 2. But remember, again, if you don't have edge, again, for example, if you have KMN, where let's assume M equal to 0 or N equal to 0. Okay, means you have KMN where M equal to 0 or N equal to 0, then the chromatic number will be 1. Again, the same thing. So the chromatic number will be, okay, because this is a bipartite graph. You already know this is a bipartite graph. So that is the reason I can say like this. But if you have, for example, if your graph is like this is also complete bipartite graph. This graph is also complete bipartite. This is K3, 0. So for this graph, the chromatic number will be 1, only one color you need. Okay. And if you have at least one edge, means, okay, then the chromatic number will be 2. And what can you say about the question number 7? What can you say about Qn? What can you say about your hypercube graph? This is your hypercube graph on n vertices. So what can we say about this Qn? Let me tell you one thing. Whenever I tell you about Qn, what comes to your mind? What should come to your mind? Whenever I say Qn, what should come to your mind? Bipartite. Remember, okay, most of the time, remember, most of the time, okay, we do analysis of Kn. Okay, we do analysis of Kn from bipartite point of view. We do analysis of Qn, okay, from bipartite point of view. From bipartite point of view. Because this is a bipartite graph. You already know this point of view. This is your favorite bipartite graph, this Qn. This is your favorite bipartite graph. Okay, in this bipartite graph, what we have, there is something called a odd parity, even parity. This concept we have already seen. All the odd parity vertices will be here. All the even parity vertices will be here. Okay, so all the odd parity, even parity vertices will be like this. So this is your bipartite graph. And because this is bipartite graph, so what will the what and so tell me, what will be the chromatic number? The chromatic number will be 2 as long as n is greater than equal to 1. But if n is 0, like q0, then the chromatic number will be 1. Because remember, q0 means only single vertex. Q0 means a single vertex. Q1 means like this. This is Q1. And Q2 is like this. And Q3 is like this. Okay, so this is the idea. So you can notice, remember, this is a bipartite graph. You already know this. This is a bipartite graph. And if you have n is greater than equal to 1, then there will be at least one edge. Then the answer will be 2. And if n is equal to 0, then the answer will be 1. Okay, clear? All these points, are they clear? So did we leave any graph? Yes, wheel graph is there. Okay, so let's see the wheel graph. What can you say about wheel graph? Wn. How many vertices? This is wheel graph on how many vertices? This is a wheel graph on n plus 1 vertices. So tell me, what is the chromatic number for wheel graph? For wheel graph. So you can notice, for wheel graph, you can think like this. See, there are two types of wheel graph. One is Wn, okay, which we get from odd cycle, where n is equal to odd. And one is Wn, where n is even, which we get from even cycle. So this Wn, where n is odd, this we get from odd cycle. It means there is an odd cycle around you. It means there is an odd cycle around you. There is an odd cycle. It means there is an odd cycle here. You have an odd cycle here. And there is a vertex here. And this vertex is adjacent to every other vertex. Tell me one thing. Can you reuse this color? Can you reuse this color? This color can you reuse? Because this vertex is adjacent to every other vertex, you cannot reuse this color. This color we cannot reuse. Okay, so for example, let me give red color to this. Now I cannot reuse this color because this vertex is adjacent to every other vertex. And outside, what you have? Outside there is an odd cycle. And for this odd cycle, how many colors you need? For this odd cycle, how many colors you need? So for this odd cycle, you need 3 colors. For this odd cycle, you need 3 colors. And there is one color here. So finally, I can say that this will be, chromatic number will be 4. Chromatic number will be 1 plus 3. I can say. Is this clear to everyone? Let me know. Because remember, you cannot reuse this color. Because if I give color number red here, then this vertex is adjacent to every other vertex. So I cannot reuse this color. And the odd cycle, we already know. For odd cycle, the chromatic number is 3. For this odd cycle, the chromatic number will be 3. And in this situation, what will happen? There is an even cycle. There is an even cycle. You already know. Okay, so this is your, I can say this is an even cycle. And there is a middle vertex. This middle vertex, you cannot reuse the color. If I give color number red here, and for even cycle, how many you need? Only 2 you need. So finally, here the answer will be, chromatic number will be 1 plus 2. So the chromatic number will be 3. Okay, so finally I can say, for Wn, what will be the chromatic number? The chromatic number will be 2. Chromatic number will be 3 when n is even. When n is even, means when you have outer cycle, this outer cycle you have even. And if n is odd, then the chromatic number will be 4. For example, if you have W3 is same as what? W3 is same as K4. You already know. So because W3 is K4, so how many colors you need? So that how many colors? Or 4 colors you need. Okay. So very simple. So this is your W3. Your W3 is actually like this. This is the W3. Now you can notice that this color I cannot reuse. Okay. If I give this color here, I cannot reuse this color. So for outer cycle, I need three colors, you know, because there is a odd cycle. Outer cycle is odd cycle. So I need three colors. Okay. And the middle color I cannot reuse. So that is the reason this, when n is odd, so then you will need chromatic number equal to 4. And when n is even, then chromatic number will be, okay, 3. So all the graphs we have seen, the pentagon means cycle of length 5. The chromatic number will be 3. So for any odd cycle, the chromatic number is 3. Okay. So this graph, what is this graph? Can anyone tell me? This graph is your W. This is your wheel graph. This is W4. And for this chromatic number will be 3. You can check it out. The chromatic number is 3 because we cannot reuse this color. This middle color we cannot reuse. And outside you have a even cycle. Outside there is a even cycle. For even cycle you need two colors. Okay, this is chromatic number 2, and for this chromatic number will be 4 because this is your this is the idea. So remember, k vertex coloring means at most k colors you need. Okay, this is not k5. Is this k5? Arpan, this is not k5. K5 means every vertex is adjacent to every vertex. Are they adjacent? Are they adjacent? This and this, are they adjacent? They are not adjacent. These are not adjacent. So this is not K5. These two vertices are not adjacent. These two vertices are not adjacent. Okay. So anyway, this is the idea. So this is the idea of coloring. So remember, if you have this graph, then coloring means that adjacent vertices should get different colors. Tell me, if you have isolated vertices, we don't care. They can get same color, different color, but adjacent vertices should get different color. Okay, adjacent vertices should get different color. So this is the idea.